My name is Sue McLaughlin, and I am chair of the Hamilton Amateur Astronomers. And tonight we have a very exciting speaker for us, and we'll get to him in just a minute. So welcome to everybody. Is there anyone who's here for the first time other than Jim? Oh, awesome. Welcome. Make sure you speak to myself tonight before you go so I can welcome you to our club and welcome to everyone else. I want to say that there has been a mix-up in the invitation that went out to our Zoom friends. Somehow I sent the wrong link to Chris and the wrong link went out. He's resent the link, so hopefully people will see it and will be able to come and join the meeting. So tonight, we'll start with our announcements. So last week we had $91.40 donated to the food bank, including one bag of food, which was a lot more than the one can of soup we had the month before. The Event Horizon newsletter deadline is Tuesday, May 28th before midnight. And thank you to Bob for doing an awesome job putting that together. It is always a fascinating read. And I love looking at all of the pictures that people send him. So thank you very much for that, Bob. A couple of things that are coming up. So the HAA Summer Picnic is going to be on Saturday, August the 24th. And it's going to be a potluck picnic and bring your own drink. Oh, I'm sorry, August 10th, thank you. August 10th, 2024. And Matthew's going to talk more about that a little bit later on. And following the picnic will be our public Perseid night. Both of those events take place out at Binbrook, and volunteers will be needed. And again, Matthew will be speaking about that in more detail a little bit later. The HAA Dark Sky Star Party registration opened up on the 27th of April. And as of this point in time, there's probably about 18 or 19 people registered to go this year, which is us. It is on a property called Andromeda Meadow, east of fee covers the cost of that. And if you're interested in joining us on the Labor Day weekend, you can go online to the website. Registration information is right there. And I know there's a number of you in the room who have already sent in your registrations. So thank you to that. So Denise and Melanie wanted me to let you know that all of the library books are due back at the June meeting, which will be next month. That's so they can finish their inventory and see what we have not had returned this year. Hopefully they haven't lost much. So if you borrowed something this month, please bring it back next month. And if you've forgotten to bring something back, you've got till June, the meeting, to bring it in. This summer, we have an awful lot of summer education outreach events planned. There are probably approximately 8 library presentations planned with the Hamilton Public Library. These are adult and youth presentations, and the small team of education outreach people are looking for maybe a couple more people who might want to help out with these. So the adult presentations do not need a police check, but the youth presentations do, and the library does ask us for the police checks for the people who are going to be involved. If you are interested in helping out, Dee is sitting at the back table. You met her when you came in. Please go and speak to her, and she can give you all of the details regarding these events. And Joanne Salchi's not with us tonight, but when she's back on, I think she's back on the 16th, you can contact her as well for more information. So there's a whole bunch of these throughout the summer. It almost seems like COVID ended. We had the eclipse and suddenly the library wants us to come out and do presentations. We've also been approached by the Burlington Public Library as well. So if we want to honor these requests and be able to fulfill them, we need a few more hands on deck to do that. The Rotary Club has also contacted us, and Friday, August 6th, they're having a fundraiser from 6 to 10 at Pier 8 in Hamilton. It's behind the Williams Coffee Pub. Matthew? It would have to be a 9. Okay. I put 6 and I must have been thinking 6 p.m. and just put 6 and 6. All right, it's the 9th. It's Friday, August 9th. It's at Pier 8 in Hamilton. And Dee and Joanne are going to go. They're going to do some solar observing while it's still light, and then look at the moon, because at that point in time, it doesn't get dark until much, much later in the evening. So if you would like to volunteer to join them at Pier 8, they're only looking for a couple more people. They think 2 or 3 more, and that will be able to cover that event. So again, Dee's sitting at the back table, and it'd be great if we could spread the workload around a little bit. So any questions about any of these outreach events for the summer? Okay. All right. Our next meeting on Friday, June the 14th, Benjamin Law is going to be here with us in person, and he's bringing his young family with him, which will be awesome. And he's going to talk to us about astrophotography in the city. Ben is a physics educator and an avid astrophotographer. He is going to talk about his passion for taking photographs of the night sky. He's going to share his tips and techniques for taking pictures in a light polluted environment. He lives just north of Toronto, and this is one of his images taken from his backyard. And the Pleiades turned out very well. So he can't always get to a dark sky spot. So he's going to talk to us about how he copes with that on Friday, June 14th. Binbrook, we have a date tentatively for tomorrow, May 11th, but I just talked to Jeff and we looked at Astrospheric and it looks terrible for tomorrow night. So tomorrow is canceled. We will send out a message to the club about that. The next option in May is the 18th, and then we've got 4 dates in June upcoming. So hopefully one of them, or hopefully 2 of them, the weather will cooperate and we'll be able to get out to Binbrook. So tomorrow, May 11th, I'm getting my dates mixed up tonight. Tomorrow, May 11th is canceled due to weather. All right, this brings us to tonight's guest speaker. Our speaker tonight is Dr. Chris Jillings, and he is going to talk to us about how to know the universe from a hole in the ground. Dr. Christopher Jillings is a research scientist at SNOLAB, studying neutrino physics and searching for dark matter. He grew up in Regina, Saskatchewan, and studied undergraduate physics at McGill University. After completing a master's degree at Queen's University, he took his first, again, I made a mistake and I'm reading it. Okay. He took this opportunity. He took a break from research to teach IB physics at Gdynia, I think I said that correctly, Poland in the early 1990s. Upon returning to Canada, he started his doctorate under the supervision of Professor Art MacDonald at Queen's University, where he worked on the Sudbury Neutrino Observatory. Upon completing his PhD, he took postdoctoral positions at UCLA studying cosmic rays, and then at Caltech working on the Camland and Daya Bay neutrino experiments. Between those 2 postdocs, he taught physics and astronomy for 8 months at the Los Angeles College. In 2006, he took on a scientist position at SNOLAB, mostly working on the direct detection of dark matter. Christopher is an avid curler, something he and I share, and a baseball fan, something he and I share, and would really like to know how a curling rock curls. So would I. But he told me that seriously, no one really knows that. So be warned if you ask him about curling rocks in the Q&A. Please welcome Dr. Chris Jillings.
Thank you very much for the kind introduction, and I'm very pleased to speak to you today. And if I can just start out by saying how impressed I am at the activities of your club. I mean, your rundown of your summer agenda is impressive, and it's great to see that enthusiasm and great to see that public outreach. Um, okay, so I'm going to talk about, as I say, how to know the dark universe, or how to know the universe from a hole in the ground. And um, so what I want to talk about today is a few things. So I'm first going to talk about why we think there is a dark component to the universe. And then once I've hopefully convinced you that there is one, I'm going to ask, what do I mean by dark? And how do you measure something you can't see? One of the big problems with that is conventional radioactivity. And then I've kind of got a day in the life video that we're going to show. And this picture is going to come back, but this is colleague Marco, who's behind a multi-stage dilution refrigerator. So the very top level that you see on this screen, I don't know if my cursor is visible, will be at liquid nitrogen temperatures, and each of these levels cools down, and this is just at a few millikelvin here at the bottom. And I'll explain why that matters in about 45 minutes. So yeah, I want to keep it to an hour, which means I'm going to be leaving a lot out, and I'm leaving out neutrinos completely. This is the only mention I'll give of my PhD supervisor's Nobel Prize. There's a lot of great underground science that goes on that I'm not going to touch on. Turns out that low radioactivity environments are good for quantum computers. Biology in ultra low radioactivity environments is actually a really interesting field. Evolution kind of tuned us to natural ambient levels of radiation. What happens if there is none? And there's people at SNOLAB doing things like growing fish and various cell lines in very low radioactive environments. I am only going to go at a few dark matter concepts. I'm not going to hit them all. So this is sort of apologies to my friends whose experiments I'm not going to mention. And there are two components to the dark universe. So if you want me to try to explain to you dark energy, that's not going to happen because I don't understand it myself. I'm in good company on that. Not many people understand it, perhaps zero. So what I want to do to motivate dark matter is, now I am going to kind of hide my screen so that I won't be able to see if there's a hand up or anything. So Sue, please just interrupt me if something's not right.
Or Chris, we can save questions till the end if
Okay,
that works for you.
sure, that's just fine.
Okay.
So we know how gravity works in our solar system, right? I mean, Kepler and Newton, those rules work with amazing precision. And I mean, the one obvious example of that is Jupiter's about 5 AU from the sun, and its period is 12 years. And if you do the math, that's the right answer. 5 square root of 5 cubed is about 12. Okay, so that's very nice, and it makes sense. And of course, if you go from Mercury all the way out to into the Kuiper belt, 68 AU away, you follow the Kepler-Newton rules. And we understand gravity in our solar system. It works perfectly. And that makes sense because our solar system is basically the sun, Jupiter, and the rest are negligible details. So we have a fairly simple system. All the mass is concentrated in the center. And Kepler-Newton works. So let's go one scale out. Let's imagine that we're not going to look at the solar system, we're going to look at the galaxy. So we're stepping up to that scale. So here's a picture of M33, and we want to ask the question, how do the stars in M33 move? And so if you just imagine it, okay, that it's not all right in the center like our sun, but it's spread out a little bit. So you look at the visible disk of the galaxy, and you can expect the velocity of things going around the center of the galaxy to follow this white line based on applying Kepler and Newton to the galactic scale. And so you look at that, and it's not even close, right? The rotation speed of galaxies is so fast that or the rotation speed of stars around the galaxies is so fast that there's no way the gravity is strong enough to hold it in. There has to be something else holding these stars in. It can't just be gravity. If what we see is everything. And even if you look a little further away from the galaxy, the 21 centimeter hydrogen that's looking at radio waves from an excitation in the hydrogen atom, and that continues on right along all around the galaxy. They're traveling just too fast, and they should not be gravitationally bound based on what we can see and Kepler knew. So the discovery of this behavior was made by one of the true greats of the last century astronomy, Vera Rubin. And this is a photo of her working at Kitt Peak, where she did a lot of this work. Still had an eyepiece, I noticed. Yeah, she was an absolute true great. She's the one who noticed this. She noticed it first in one galaxy, and then went back to work and created an enormous catalog of these galactic rotation curves, as they're called, these curves at the speed of objects going around galaxies. And you measure that with the Doppler shift of the lines, right? We know the Doppler shift, like from race cars. There's Doppler shift also for light, and if a star's moving away from you, the light looks a little redder than if it's coming towards you. And based on those Doppler shifts, you can work out the speeds of objects. Okay, so that scale. Let's go to the scale of a cluster of galaxies, and this is the Coma cluster. It's taken by Spitzer very recently. And Zwicky in 1933 found the first evidence for dark matter, and he showed that the Coma cluster had too much kinetic energy given the amount of gravitational potential energy in the system. And basically, that's a $100 way of saying the galaxies are moving too fast for gravity to hold them together. So even on the scale of clusters of galaxy, we have the same phenomena. And one of the best examples of this, and this one's going to take a little bit of talking through, is the so-called bullet cluster. And there's a nice write-up in the astronomy picture of the day. And you'll notice I crib a lot of my pretty pictures from the astronomy picture of the day. If the internet only had one site, I think everyone on this meeting would hope that would be it. So red is X-ray emissions, and you can see this shockwave thing at the front. It has traveled through the other cluster of galaxies, and it's been deflected back, as you would expect something traveling through something else to do. And you can see that it's here. But if you look at the blue is inferred from doing gravitational lensing. So this bullet cluster is between us and some of those background stars. And by looking at how the light of the background stars is bent by gravity, you can work out where there's lots of matter in between. And that's colored blue in this picture. And you can see that the dark matter, the stuff that we don't see, we have to infer, has traveled as the two clusters hit each other. The dark matter just traveled straight through, whereas the ordinary matter, the X-ray emissions, show signs of an interaction. So that's a great clue that dark matter can't interact much. And I love this picture. It's a little bit old, but this is from the Sloan Digital Sky Survey. So basically the Sloan Digital Sky Survey is a telescope that highly computerized data pipeline, and it took pictures of the sky and images of the sky and worked out where things were. And so it drew these pictures. Each dot in this picture is a galaxy. And this is like the parts of the sky it can see. I believe Sloan is in Arizona. And we're right in the center. And as you go further out, you're getting farther away. They measure distance in cosmological redshift. But let's, this outer circle is about 1.8 billion light years away. And you'll notice that this looks like an open-celled foam. Now, an open-celled foam is not beer foam. Beer foam is each little bubble is closed. An open-cell foam is kind of like a sea sponge. where the pores kind of move into each other and you don't have closed pockets. This structure you can get if in the early universe you have more gravity seeding the gravitational clumping of things. So we've looked, but you can't get this structure just with ordinary matter. The computer simulations don't work. You don't build up these sort of strands, this open cell structure. So we've looked at the universe on several different scales, right? We look at our solar system, galaxy, clusters of galaxies, cosmological scales. I left off the beautiful pictures of the cosmic microwave background because that, but again, on the scale of the early universe, we can't make sense of it unless there's more mass than we can see. So what do we need? And this is one way to make sense of these data. So there's a component of the universe we cannot see. Okay. And that this material does not interact much with normal matter, or we'd have seen it. It had to interact in this model in the early universe to get created. When the universe is very hot, the interactions were more likely. So, but as the universe expanded and cooled, it basically dropped out of normal interactions with material, only interacting with gravity and the weak nuclear force very rarely. The density of this stuff has to be so small that if you integrate up on the scale of the solar system, the mass is negligible compared to the sun. But if you integrate up on the scale of a whole galaxy or a cluster of galaxies, this stuff adds up to about 5 times more than normal matter. And the reason this works was explained best by Douglas Adams with this quote that you can all probably knew by heart, that space is big. You won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts compared to space. Because the universe is so big, there's so much empty space and galaxies and whatnot, there's room for this dark matter to add up, even though if you take a small section of space like our entire solar system, it doesn't add up to much. So one thing we are absolutely terrible at in what we do is coming up with acronyms for things. So what I'm describing we call a WIMP, or a weakly interacting massive particle. And what does that mean? Well, if you're going to explain something you don't understand, you don't want to invent like 2 miracles at once, right? We'll just keep it to one new thing. So the dark matter needs to create it in the early universe.
I'm leaving.
Hi, am I still audible? Okay. So we want to assume that it interacts with ordinary matter using forces we know about. We're going to invent a new particle. Let's not invent a new force. It interacts under gravity. That's all I've been talking about so far. And let's have it interact with the weak nuclear force, which is responsible for beta decay. Say, if you get a PET scan, the beta plus decay in a PET scan, that creates the positron and positron emission tomography. That's a weak nuclear force process. Neutrinos also work with the weak nuclear force. So the stuff gets created in the early universe when the early universe is hot. It interacts with normal matter, but then as the universe expands and cools, the weak force becomes less and less relevant, and then the dark matter really mostly only interacts with gravity, mostly. And then the dark matter, though, which is interacting with gravity, starts to seed the clustering, and that leads to the clumpy structure of our universe. And this is the WIMP model. And it's not the only dark matter model, but it's the simplest one that is consistent with all the data so far. So I said there wasn't much of this stuff in our solar system, so how are we going to find it? What do I mean by the density is low? Well, in the conventional WIMP model using conventional descriptions of our galaxy. The density of WIMPs is roughly equal to the density of one hydrogen atom per 3 cubic centimeters. That's astonishingly small. So the number of WIMPs near the Earth that we're trying to measure depends on how heavy each WIMP is. So if each WIMP had a mass of 300 hydrogen atoms, there would be 3 WIMPs per liter in the room you're in. And again, that's an astonishingly low density. Okay, so something is going on with our universe. Kepler and Newton do not explain the universe unless there is something we cannot see in the universe. So I want to ask the question a little bit, what do I mean by dark? And I want to ask the question, how do we measure what you can't see? And on the left there, that's Cedric Lewis, an engineer in training on the project I'm on, and Adam Wind, an undergraduate student, installing high purity argon piping. And I'll explain why we like argon in probably 20 minutes now. Okay. Dark matter is a term of ignorance, right? We don't know what it is. So what we're really saying is it doesn't produce, reflect, or block light, right? If you have an old school electric stove and you turn the element on, the element glows. Dark matter won't do that. You can't bend dark matter with a magnet, or you can't detect it with electricity, or we'd already see it in our telescopes. We need our old friend, the weak nuclear force in the WIMP model. And the weak force is how neutrinos interact. And as I say, it's responsible for the beta decay of some radioactive isotopes, notably, as I say, the PET scanner positron emission. So it's time to think about curling. And so that's Tracy en route to winning the World Championships this year. And she's throwing yellow rocks. So let's imagine she's throwing a takeout. Okay, so she's going to throw a takeout. She lets a rock go. It's sliding towards the blue rock. And there's a collision, and her rock goes one way and the blue rock goes the other way. Fine. So this is the dark matter version of that. You see the blue rock, that's an ordinary atom in your detector. And there's dark matter heading towards it, but we don't know. And then the something in our detector recoils. And that's it. That's all we see. So the principles, though, aren't really that different than hitting a curling rock. You have some interaction. I mean, it's not the force of granite on granite, but you have some interaction. You have some effective size, that the nucleus is a certain effective size to the dark matter. And when the dark matter hits it, it's going to have to obey the rules you learned in high school physics. It's going to have to conserve energy. It's going to have to conserve momentum. So there's something about the recoil you can use to learn about what the dark matter is. And this is important because there's a real big caveat here. We don't know how heavy the WIMPs is. In curling, you've got like mass objects hitting each other, right? Like the two stones weigh the same. So if you hit it dead on the nose, your rock stops, the other one keeps going. But we don't know in dark matter if the collision is like the top, where you've got a lighter thing hitting your atom, or if you've got a very, very heavy object hitting the atom. So you have to be ready for both scenarios. And the effective size of an atom, as seen by dark matter, we don't know. And it's not, in some sense, a geometrical size. Like if you learned a nucleus is about a femtometer across, yeah, that's true. And that's the effective size of a nucleus if you're going to bombard it with neutrons. Okay. Interestingly, the effective size of a nucleus, if it's on its own, with nothing else in the universe around it, and you're going to bombard it with an electron, is infinite, because the electromagnetic force extends forever as 1 over r squared. So the effective size of the atom as seen by dark matter, it's not the geometrical size of the atom. But those are the two things we need to keep in mind as we're trying to understand dark matters is how big is it, and how likely is it to interact with the nucleus using the weak force. Since we don't know that, we actually want to do as many targets as possible. So we're sensitive to the kinematics. And I'm going to talk about 3 in my talk today, although my colleague on an experiment literally right beside mine, he uses hydrogen as a target. But silicon or germanium crystals make a great target. Liquid argon makes a great target. And interestingly, so does fluorine. And I'll briefly go through how some of these actually work. This is actually, I think this particular photo is a germanium crystal, but if you made an extremely pure crystal of a semiconductor, and a semiconductor is a device which normally does not conduct electricity unless you give it a little kick of energy, and then you can promote electrons where it becomes conducting. And the other thing about these crystals is they're extremely regular. So even if you hit a nucleus of an atom, you can actually, that vibration traveling through the crystal, when it hits the top surface, you can put sensors on the top surface that measure that vibration. Now, I just talked about vibrating a single atom and measuring that as it travels through the crystal. So for that to work, this thing has to be really, really cold, or otherwise normal thermal variation would completely wash out any signal. And that's where this fridge comes from. So these crystals actually are going to get mounted to the bottom stage of this crystal, which is only, or this fridge, which is only a few, maybe 10 millikelvin above absolute zero. So the very top stage of the fridge, you heat it with, or you cool it with liquid nitrogen, and you get to about 77 Kelvin with that. That's fairly easy. And then you work your way down in stages. One of the stages will be about 4 Kelvin, and that's, I think, the next stage. And you get 4 Kelvin by using helium-4 as your refrigerant, boiling and liquefying helium-4. And actually, the way you get down to the lowest stage here in a fridge like this is dissolving helium-3 into helium-4. So some of you who've maybe done some chemistry know that if you dissolve acid in water, it heats up just by dissolving it. And that's why you always add acid to water and not water to acid. And that's just the act of dissolving one substance in another can either absorb or remove heat. Turns out that's true for dissolving helium-3 and helium-4. And the dilution of helium-3 and helium-4 releases energy. And so you can use that in the final stage to get down to millikelvin. It's really cool. The reason that is so pretty is that fridge absolutely cannot tolerate any tarnish on it, or it will not work. So there's a very thin layer of gold on all the metal surfaces. Fluorine is actually a great choice, and the technology goes back decades. But if anyone here cooks pasta in a really, really smooth stainless steel pot, you'll know that if you heat up the water, you can actually get it a little hotter than boiling. And if you then throw in some salt or disturb it, it can boil quite quickly. And this is called superheating. And so if you took a very, very smooth glass flask and filled it with a superheated liquid, in this case, C3F8, when some subatomic particle, some radiation goes through it and bounces off an atom, that gives that little atom a kick, and that forms a nucleation site, and you get a bubble going. And so what's happening here, and the reason there's so many bubbles, is this was a calibration with a neutron, where a neutron bounced through the fluorine many, many times and created a bunch of little bubbles. And they can measure the pressure change, and then they take pictures with the camera, and they get all sorts of information, and they can reconstruct where the bubbles are. So that's a pretty slick technology, and that's being developed. Liquid nobles, argon and xenon. I work on a liquid argon experiment, so I'm going to use that as the example, but the idea is similar. Argon is a noble. It just wants to be a single atom, right? It doesn't want to do chemistry. But if you deposit energy in it, for say from some type of radiation hitting it, a gamma ray, an electron, dark matter, whatever, you can hit the atom, you can make the atom, you can deposit energy in the atom, that atom recoils, it hits other atoms. You get a little bit of local chemistry happening because you've added energy. You can make an unstable argon-2 molecule. And of course, it doesn't want to be an argon-2 molecule, so it decays and it emits ultraviolet light. And we put some special coatings on the inside of our transparent acrylic container that absorb the UV light and re-emit in the blue, and we measure blue light. So I guess in that very indirect way, we do measure dark matter with light, but only through liquid argon as our intermediary. So there's something we've never detected that we're going to claim exists, and we're going to try to measure it. The most important question is, how do we know that if we see a signal in our detector, that we're not measuring conventional radioactivity mimicking a dark matter signal? I mean, I showed you a signal in a detector using a neutron. How do we know that it's just not conventional radioactivity mimicking our signal? And we spend probably 50 times more answering this question than we do imagining trying to work out what the signal is. So I'm going to then get to the next part of my talk, which is how we deal with conventional radioactivity, and that's my friend and colleague Pierre. We're going to get a different photograph of this glove box. There's a gate valve on top of this glove box, and that he's taken off. The glove box is here. Each of these ports here that seems to have a blank door on it has gloves behind it, so that we can reach in and work in a radon-free environment. And this photo kind of gives you a sense that these experiments are built to fairly large scale, some of them. And one of the tricks of doing, or one of the challenges of working with these experiments is doing kind of industrial level stuff along with very delicate stuff, and making the two coexist side by side. Okay, so the first thing I want to talk about is cosmic rays. And so once again, I've cribbed an image from the astronomy picture of the day, and this is an artistic rendering. So Pierre Auger first worked out the concept of a cosmic ray air shower. And what he did is he put some detectors on the ground a certain distance apart, and he noticed that much more often than should happen by chance, he got a signal in the two detectors at the same time. And he realized that what had to be happening there is that there was some fundamental primary particle hitting the atmosphere at very high energy, and that particle was smashing into atoms in the atmosphere, which was then the resulting cascade of particles smash into particles in the atmosphere, which creates more, and you end up with an air shower. And of all the particles in the air shower, the two that would bother us the most in our experiments are neutrons and muons. A muon is the heavier cousin of an electron. It has the same charge as an electron. It has the same intrinsic properties, except for its mass, and it's a couple hundred times heavier than an electron. So it's actually a very penetrating particle, and it can go through the Earth. And right now, in each and every one of your brains, there's probably 20, 30 muons per second going through your brain. And these particles are quite penetrating. So the way we deal with that is we go deep underground at Vale's Creighton mine in the Canadian Shield, and the rock filters out the muons. So in more conventional units than muons passing through your brain every second, there's about 100 per square meter per second muons at ground level. And there's about 3 muons per square meter per day deep underground at SNOLAB. And now that I'm talking about SNOLAB, I want to take a moment to say that SNOLAB is on the traditional territory of the Robinson-Huron Treaty of 1850, shared by the Indigenous peoples of various Anishinaabe nations, including the Atacamishang Anishinaabe First Nation. We acknowledge those who come before us and those who are caretakers of the land and the waters. And this photo is a photo I took. It's just east of Laurentian University, about 20 kilometers from SNOLAB, also in the Robinson-Huron Treaty. Now, I just described that we need to worry about conventional radioactivity and keep these detectors very pure, so we go deep underground, but mines are astonishingly dirty places. So I'm going to take a couple of minutes and let you see how we deal with that. So yeah, it's a shower every day when we get down, and the only place we keep food, of course, is in the lunchroom. But it's actually a fairly once you're a few feet underground, it's like being underground anywhere. Um, I took Tanya, my wife, on a tour once, and she said that the mine was more interesting for her because once she got into the lab, it just seemed like a lab with no windows and odd-shaped walls. Um, so we want to keep radiation away from our detectors, and this is actually my colleague's experiment that uses a gas target inside this copper sphere. So copper is, because you can do electrochemistry on copper, and basically you've got copper ions in a bath of acid, and you can drift the copper atoms from one side to the other and collect them. But if you play games with how you do that, you can separate out contaminant atoms from the copper so that you drift the copper at a certain speed, and you keep only the copper to very high purity. So that inside there's a gas target. They're looking for dark matter. It's surrounded by a copper sphere, which is quite thick, and that provides shielding. And the really cool thing about this target is it's then surrounded by lead. And you think, okay, well, lead's a conventional gamma ray shielding, but this lead is special. This lead was on a sunken Roman ship. I mean, not quite literally. It was on a Roman ship that sunk a couple of thousand years ago in the Mediterranean. And the reason that's important is there's an isotope of lead, which is radioactive, lead-210, and it's created by cosmic ray interactions in lead. So the same cosmic rays that we go underground to get rid of, this lead on a Roman ship has been protected from the cosmic rays producing it for 2,000 years. And this lead has a half-life of 22 years. So 22 years is actually a pretty terrible half-life. It's active enough that you get an appreciable rate, but you can't wait out 22 years, right? The lifetime of an experiment might be a decade or two. So having this undersea lead from ships is fantastic. And then the outer layer of lead is conventional lead, like well-cleaned lead from a mine. And then we have, and that's how they keep gamma rays out from there. The plastic is actually really important because that keeps neutrons out. So yeah, neutrons and plastic. So this is a picture of Deep 3600, and we've got our very cold liquid argon. We've got our acrylic surface, and our PMTs actually are the most radioactive component we have in the experiment, so we pull them far back. Also, PMTs want to operate warm, not cold. They are light sensors, sorry. These are light sensors. There's photomultiplier tubes in yellow. So we pull them back through pieces of acrylic with reflective sides, and that keeps the neutrons from the PMT glass away, and it keeps the light sensors, the PMTs, warm. And we put plastic shielding in between. Now, why do we use plastic and water for shielding against neutrons? Well, a neutron weighs about the same as a proton. So it's like billiards. If a neutron hits a hydrogen atom or proton, on average, half the energy goes into the proton, and you slow down the neutrons very quickly. If you throw a marble at a bowling ball, the marble goes scattering away, but it doesn't really slow down. And if you throw a bowling ball at a marble, the marble goes flying, but the bowling ball keeps going. So if you really want to block neutrons quickly, you use water. Or in the case of a CANDU reactor, heavy water, deuterium. But you want approximately equal weights to slow down neutrons. And we also built our detector, which I'll talk about a little bit more about. It's in a large water tank, and we can make the water, make the water. We take the water and we purify it to very high purity, and it's inexpensive, and it in itself is very, very clean. So the other thing too is we need to choose the cleanest materials we can. So like I showed the pictures and said that the most radioactive thing in our detector was these light sensors. So we had to pull them away to understand, to keep the radiation away from our our experiment. And the way we knew that is we counted them using gamma ray counters or radon emanation chambers, or sometimes detectors that look for alpha particles coming off surface, or chemical techniques like ICP-MS, inductively coupled plasma mass spectrometry. Don't ask me chemistry questions. It doesn't go over very well usually when I try to pretend to be a chemist. So everything we put in deep was radioassayed, and we looked for uranium and its progeny, thorium and its progeny, potassium-40, cobalt-60, all of it. And because we're in a mine, and the mine rock itself is about 1 part per million uranium and thorium, just naturally, that's why we keep the lab so clean, to keep all that potential source of background away from the experiments. So this is what the inside of this gamma counter looks like. There's a germanium crystal in here, which is a very sensitive, precise measure of radioactivity. And we put our samples around it. And this little pipe you see coming out here surrounds a sample with nitrogen gas that's been boiled off from liquid nitrogen, and it has basically no radon in it. So we get a very clean measure of radioactive backgrounds in our materials. Yeah, radon is the worst. It's just like the worst. Why? Well, it's a gas, so it gets everywhere, right? It has a half-life of about 4 days. So if there's any radioactivity somewhere, like in the rock in the mine, the radon can get out and get in the air. The radon itself decays to progeny that are themselves radioactive, ending in this lead-210 that has a 22-year half-life and is a bad background to our experiments. So the radon levels in Creighton Mine are very low by human health standards. It's not an issue for us or our lungs or anything like that, but it's definitely an issue for our detectors. So our detector systems are very often vacuum tight, and we use purge gases like boil off nitrogen when we need to work at atmospheric pressure to keep gas away. And this is our glove box. Each here are glove ports, so we can work through rubber gloves to keep the gases out. And you see a whole bunch of vacuum flange connections in there that we have to make through gloves. So the other thing I really want to mention about building the experiments is the amount of effort that goes into it from different skill sets. Yeah, I mean, there's the scientists, the physicists, and the chemists who, at some fundamental level, design it. But you can't make it work without engineers. Okay, these projects run for typically a couple of decades, and yeah, to get the value out of them and have them work right, you need project people keeping on top of you and making sure that things are getting done. You absolutely need skilled tradespeople. I can't emphasize that enough, that millwrights, electricians, machinists. So like on the right, I've got a picture of a couple of SNOLAB millwrights who are, installing a hoist inside this tube for lifting part of our detector in and out, up on scissor lifts doing that. Scientists can do some of the light stuff on the scissor lift, but you certainly don't want us rigging very large, delicate things. And the other thing is we need logistic staff. The people who keep the lab clean, the people who deliver stuff underground from surface, the people who make sure that, that stuff works. And that is a big job. And all of that is needed to make these things work. So we built Deep 3600 and we took data for 3 years, and we saw no evidence for dark matter. We did, despite all our care we took for backgrounds, we were surprised by a couple of potential sources for background. So what I'm spending most of my time on right now is after our 3-year data taking run is we're doing a couple of hardware upgrades that we think will eliminate those backgrounds and allow us to continue. Based on what we measured and for how long we measured it, we were able to put pretty good constraints on our ignorance. If you think about how heavy dark matter is and how likely it is to interact with atoms, we were able to say, yep, we know for sure there's no dark matter there in our map of where to look for dark matter. And we learned what we would need to do to keep looking for it because there's lots of ways dark matter can still exist. And we have to understand what we measured, how well we did it, and what we need to do to carry forward. And that's what we are in the middle of now. So what we're doing with liquid argon is we're doing, there are about 4 liquid argon experiments of about the same size as ours. And we combine forces across the world. So we have a group of about 300 scientists, and we're building a large detector called Darkside 20K. That's because it's going to have 20,000 kilograms of argon in a mine in Italy, at the Gran Sasso laboratory. And we are developing a plan for a very large multi-100-ton detector at SNOLAB. The silicon and germanium experiments are ramping up. I've got a couple of friends who are working on that, and it's great to see. They're building their detector shielding, they're running their test detectors, getting early science data, and that's working really, really well. So the silicon and germanium detectors are ramping up. And one really cool technology is somebody realized that, hang on a second, if you took a very large CCD, not like you have in a camera, but in a satellite camera, some astrophysical thing. So you get a CCD that's about, I don't know, 10 centimeters by 10 centimeters, and it's thick enough. There's actually quite a bit of silicon in that, and that's a good target. And because it's a CCD camera, you can actually image what's left behind in the radiation. It's very cool. And the fluorinated bubble chamber experiments are absolutely scaling up and continuing to do more. Worldwide, more and more targets and different dark matter mechanisms beyond the WIMP dark matter model I suggested are being considered, and people are trying to measure them. But dark matter still remains a term of ignorance. We don't know what it is yet. We are still also in the situation where there is no alternative to dark matter that fit the data at all scales. In other words, no effect in the solar system, but you see effects at galactic and supergalactic scales. So right now, our best bet for understanding the dark universe is to keep looking for dark matter. And with that, I just want to say we have a virtual tour of the lab. The link is here, but if you just go to www.snolab.ca and faff about a little bit, you will find some really cool stuff that you can look at. And thanks so much for listening to me, and I'd be delighted to take some questions.
Thanks so much, Chris. That was absolutely fascinating. I'll never throw another curling stone without thinking about dark matter again.
I think
It
about
might
Tracy
mess up my
Fleury. She's
game.
better at throwing curling stones than most people in this world.
Questions? Doug, are there any questions on Zoom?
Hi, my name is Paul. I'm new to astronomy. Hang on.
Right close? There you go. Hi, my name's Paul. I'm new to astronomy. I have a keen interest though. I happened to see a bunch of physicists talking about dark matter in a conversation out of, I think it was Berkeley. I think the lady who discovered that the galaxies couldn't stay together by gravity was found back in the 30s. And that must have been a pretty exciting discovery. What do you think about the theory that we just don't understand gravity enough that's coming out of, I think it's Finland or Scandinavia?
Yep.
That it doesn't, we just don't understand the finer points of gravity yet, but it could still work. What do you think about that?
So yeah, there have been various efforts. The best gravity theory is called MOND, M-O-N-D, which just basically stands for modified Newtonian dynamics, which is a fancy way of saying tweaking gravity. So one of the reasons I was jumping up and down in my talk about at all scales, that gravity works actually not only on the scale of the solar system, but you get smaller, right? It works at the solar scale of you know, throwing an apple into the air, and the scale of the solar system, and then the way it breaks down. The modified Newtonian dynamics can't get everything at all those scales to work. Unless, and there is an unless to this, you might be able to get it to work if there is an extra neutrino, sometimes called a sterile neutrino. It seems, especially with some of the newest data from satellites, and one has to be a little bit careful with data that's fresh off the press. Some of the early data from the James Webb satellite got revised a little bit once the calibrations were complete. You can make modified Newtonian dynamics work if and only if you add something else into the mix. And there are people who make a case that if there's something called sterile neutrinos, another type of neutrino, and there have been hints of that, with modified Newtonian dynamics, you might be able to get the same thing. But on its own, it doesn't work. But of all the alternative gravity theories, it comes the closest.
We have a follow-up question.
I've been trying to figure out, and I can't find a article that's in simple layman's terms, but maybe you could help me. If light has no mass and mass is required for gravity to take effect, why does light bend when it goes through a gravitational field?
Okay, that's a fantastic question. And it's almost correctly formulated. And it's a great question. And there are two answers to it that I'm going to give. And the first answer is that gravity in Newtonian view is just based on inertial mass. In Einsteinian gravity, it's based on energy, and because the light carries energy with it, you can measure it and it can be deflected. But the better answer, I mean, what I just said was true, but it's not a good intuitive answer to the question. The better answer is to ask the question, what is gravity? Okay. And when I was teaching undergraduate astronomy at Los Angeles City College, I'd always start, I'd have a ball on the string and I'd be twirling it around in a circle, and I'd talk about how my hand was like the earth, and the rope was gravity pulling the ball in, and it was traveling in an orbit, and blah, 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 blah. And I said, so the moon goes around the earth, and then I'd ask the people, where's the rope? And they looked at me funny and said, what do you mean, where's the rope? I said, well, where's the rope? I mean, there's a rope pulling this ball in this demonstration I'm doing. What's keeping the moon going around the earth? What is that gravity? What is it? And Newton didn't know. And the idea that Newton thought it wasn't relevant is not true. Newton was actually really disappointed he couldn't answer that question. And Einstein answered that question, and that the rope is that gravity affects the geometry of space. So if you're traveling from, I don't know, London to Los Angeles on an airplane, you travel on the shortest path that you can take on the curved surface of the earth. And it looks, but you put it on a 2D map projection and it looks like you're traveling in some crazy path, but it's the shortest path that you can take. Okay. When they're doing things like gravitational lensing, right? So you've got the Hubble Space Telescope here, you've got some heavy object here, and you've got some very bright object over there, and the light comes in and it's bent. Why is the light bent? Well, the light is bent because that heavy thing in the middle is distorting the geometry. Okay, and it's distorting the geometry in a way that causes the light to travel always locally in a straight line. Light thinks, okay, we're going this way, we're going this way, we're going this way. But because the geometry of the Earth is no longer, or the geometry of the universe around that heavy mass isn't flat, what looks like a straight line to the light looks like a curved line to us. Just like, I mean, you know from high school geometry, right, that parallel lines never meet, right? Well, if you started in South America at the equator and walked due north, and you started in Africa at the equator and walked due north, those two lines are initially parallel, but because you're on a curved geometry, they will meet. Okay. So the answer to your question intuitively is the light is traveling what it thinks is in the local straight path, but the overarching geometry of the area caused by gravity forces that to be bent, if that makes sense.
Wow. Hang on.
So are you speaking about the fabric of space effect, where if you have a ball in the middle, the light follows the curve?
Yeah, basically, yeah. I mean, yeah, if I had a bowling ball on a trampoline and you throw a marble, you know, just missing the bowling ball, it bends like that. That's exactly what happens to the light. And how much the light gets hooked around by the bowling ball as we see it on the far end depends on how heavy the bowling ball is, right?
Right.
And the point of the gravitational lensing measurements is what we can see isn't heavy enough to bend the light that much. You need a heavier bowling ball than is what is there based on all the visible stars and stuff.
So in the end, the discovery that light bends because of the solar eclipse in the early 20th century wasn't actually caused by the sun, it was caused by fabric of space.
Well, yeah, but the sun is what's bending the fabric of space locally.
Okay, thank you very much.
That is the best explanation of gravity I have ever heard. So thank you. Thank you for that. People have asked me to explain it and I was like, it just is. I don't know. So thank you. I now have something to say. All right, I've got another question over here. Doug, are there any questions coming from Zoom? Yes, okay. I'm going to Doug and then to the young person we have in the audience and then to Zoom.
Hi,
Hey, Dan, what's happening with that? Okay, Doug, come on over here. There.
you mentioned muons that they come through the well, they come right through us and come through a lot of material. And I know the purpose of having the Sudbury Neutrino Observatory is to block out a lot of different radiation from space, but the neutrinos can
Yeah.
still get through that. But Is there anything you can
These
do
are the
to,
questions.
like with the upgrading the SNOLAB or whatever to block out muons more, or does that or is that pretty well been looked after?
Okay, that's a great question that has 2 or 3 different answers that are going to sound contradictory. So the first thing is actually we can't go that much deeper to get better. And the reason is if we have pretty much blocked out all the muons coming from above us, if we were to go down another couple thousand feet, we would block them out more, but we would also then you reach the point where you get muons created by neutrinos coming the other way, and it does bottom out. So the answer is, what do we do? Now, here's the tricky thing. The muon itself isn't a problem for many of the detectors because muons are obvious. Okay, the muons have very high energy. The signals they live in the detector are extremely big. But where you've got a muon, there's some chance that the muon hit something in the rock or something in your detector and generated a whole bunch of neutrons. And neutrons are really bad. So these water shielding tanks that we have are often instrumented so that if the muon gets as far as the water, even just in the water, we know about it. And because there's only a few a day per square meter, when the muon hits the water, we'll tag that in our data stream, and for some fraction of a second afterwards, we'll disregard that data for our physics analysis because there's a chance that it's a muon-induced neutron is coming through, and that's what's giving us a signal. So at the cost of, I don't know, a tiny fraction of our exposure time, we can get rid of that. But then comes the harder version of this question. I warned you were going to get 3 answers, and they were all slightly different. Sometimes a muon hits a nucleus and makes that nucleus radioactive, and sometimes that radioactivity can last for minutes. Okay, and so one of the experiments that I work on in particular, I do small tasks for it because the experiment is is in the Italian lab. It uses germanium crystals to do a neutrino measurement. It's called Legend, and it is particularly sensitive to neutrons can hit the germanium and make a radioactive germanium that has a half-life of a minute. Well, that's bad. A minute's a fairly long time, and the Italian lab isn't as deep as ours, so they would have a real problem with that. Except because they've got a detector made out of several smaller crystals, and if they do the data right, they do the data analysis right, they can keep track that, okay, the neutron would have hit this crystal. There's a signal from that. And then they only need to, if you like, veto 1 part in 50 or 1 part in 100 of the larger detector to make sure that doesn't happen. So yeah, muons can be dealt with. At one level, we've solved the problem by going deep enough because the rates are so low. At the next level of sophistication, you have to be a little bit careful to make sure that there aren't neutrons coming with the muons for the ride, but that's relatively easily dealt with. But there are experiments now where that muon can generate radioactivity itself, and that is an issue. And that's one of the reasons SNOLAB is so deep, is to make that less of a problem so that you don't need to get fancy in the analysis to work out exactly what that is. That's yeah. Great questions.
Come on up. Come on up here. It'll make it less screechy in the microphone.
Sorry. Uh, Other than like the science, other than just knowing, what is the appeal of like studying dark matter? Like, why is it important to like us?
Yeah, so so that is a terrific question. So I'm going to answer that again. Sorry, I'm going to give you two different answers. The first answer, and the most important one, is why do people dedicate their life to like singing opera or playing jazz? Right? Curiosity is some fundamentally human thing, and every society is dedicated a certain amount of resources to pure research because it's cool. Now, yes, we all know that navigation helps the military, and sailing nations and whatnot developed, it's no accident the English developed the first decent clock and figured out how to measure longitude. There are usually practical effects of what we do, and there are. The biggest practical effect of what we do in terms of like the local economy or whatever is producing good students. Because if you get students who can learn how to build these things and operate these things, they can do, I mean, they can do a lot of really cool things. And if you look at what the graduates, the students who graduate who don't go on in academic physics do, I mean, we have people building reactors, people in medical physics, people people are making isotopes, radioisotopes for medicine. There are a lot of, so the practical answer, the best practical answer is students, and that students go on and do these things. But if you were to ask me why I get up early in the morning to catch that cage, the answer is because I think it's really freaking cool, and I'm lucky to be able to do it.
That's the perfect answer, especially for getting our young people involved in science later on, because it's just so bloody cool. We are going to go to Zoom, and Brett, if you just turn your mic on, you can ask your question directly.
Thanks, Sue. Thanks very much, Chris. I really enjoyed that presentation. I know I'm going to be going back on YouTube and watching it over again. It was very thought-provoking, and it got me thinking about some of the physical aspects that you had to graze over because you only had an hour, of course. And you might be familiar with astrophysicist out of Oxford. She has a YouTube channel, and just yesterday she released a video on why do we know how much dark matter there is in the universe, and she referenced back to some of her earlier videos on the topic. So if anybody's interested in that, you just have to look up Dr. Becky.
Yeah, she's great. I didn't shout her out in my talk, and so thank you for bringing her up. She's really good.
She's right up there.
Oh no, she's really good. She does not sensationalize, and she explains things well. And if something really interesting comes up, she will tell you why you might be skeptical about it, as well as why it might be really important.
I noticed that, and coming from a scientist, that means even more, of course. But I did have a question. It might be more mundane. At one point, I understood that there was a whole bunch of heavy water that was being used in a detector. Is that still the case, or has it gone away?
Yeah, so like I said in slide 3, there were things I'm not going to talk about. And so I didn't talk about my PhD project or the neutrinos at all. So yeah, the original SNO experiment had a heavy water target, and heavy water was actually a great target for neutrinos and what we didn't know about neutrinos at the time. The heavy water has been returned, like to the gram we accounted for it, and we returned it. And the detector is now filled with what's called a liquid scintillator, and it's being used for a new type of neutrino measurement, and it's now called SNO Plus instead of SNO. And it's working extremely well. And it is still being used for neutrino physics, and in particular, a rare type of weak nuclear decay called double beta decay. And yeah, I have a lot of friends working very hard on that project. A liquid
You're-
scintillator is scintillation. It means producing light, you know, like that was a scintillating performance, you say, of a movie star. And so when radiation interacts with the scintillator, you get a flash of light out, and the amount of light is proportional to the energy the radiation put in. And as well, characteristics of the light, like its time structured, is do you get an immediate flash of light or a slightly slower flash of light, tells you a little bit about the radioactivity in the scintillator, like what type of radiation it was. But yes, it is absolutely operating and taking data and continuing to get upgraded through various phases to make a really quite exciting neutrino measurement that should be kicking off in about a year.
And I can't remember. I think I'm dating myself by even mentioning the heavy water. That goes back how far in time?
Uh
The 90s?
no, well, okay. Yeah. The detector started taking data in 99. It took data through to 2006. And it was drained shortly after that. And I say drained, I mean very slowly. The water was taken out, put in rail cars, and taken back to surface and returned. But yeah, early 2000s. And that was, I mean, that's what Art McDonald won his Nobel Prize for, showing that neutrinos had mass using the different interactions in the Sudbury Neutrino Observatory. The other cool thing for astronomers about the Neutrino Observatory is everyone talks about the neutrinos and the mass of the neutrinos, and that's very cool. And that Nobel Prize was well earned by Art. But it also demonstrated that we know how our sun shines quite accurately, that the neutrino flux from the sun actually makes sense given these standard solar models, and that, you know, humankind's 6,000-year-old quest to understand how the sun shines, probably longer than 6,000 years, got answered in Sudbury is kind of cool.
That's another cool thing. Coolness just doesn't end in this branch of science. We're going to do one more question from the room, and I know there's one more person in the room who wants to ask a question, but we're going to do one more in the room, and then Chris, if you stay online, I'm going to send the last question during the break to the headset at the back, and if you're okay, he can ask his question that way. Gary, is that okay with you? Okay, so Jeff, come on up and you can ask our last in-room question.
Thank you for being here tonight with us, Chris. My name's Jeff. You talked to earlier on about, like since Vera Rubin, studying deep sky objects that don't behave the way we think they should. Their geometry is different, their rotation is different. I guess it's clumping together in places. Does that mean that the dark matter that's causing this is also clumping? And I guess part two of the question is, has it been mapped?
Okay.
Maybe one.
You're a sharp group. Yes and yes is the short answer. So, but you want a better answer than that. Yeah, so this is, yeah, the dark matter has to be clumping. And in fact, the idea is that the dark matter started the clumping of our universe. Okay, that when the universe was hot and everything was bouncing around and interacting with each other, initially in the first little bit, because it was so hot, these weak interactions did actually matter because the things were smashing into each other so hard that the dark matter was mixed up with everything else. But at some point, the universe expanded and cooled, and all the normal atoms were still bumping into each other, completely randomizing. But the dark matter at this point already kind of quit interacting, and it started, because it quit interacting, gravity could with the weak and strong and electric forces and whatnot, or in the case of dark matter, quit interacting with the weak force. the dark matter could start clumping and gravity would start bringing it together. And that clumping started before we started appreciably clumping the atoms. And so, yes, dark matter is clumped. We don't know exactly how, and it's actually a relevant problem, because when I said there was about a 1 proton per 3 cubic centimeters mass of dark matter in our local area, I think I threw in the word in the conventional model of our galaxy, right? If for whatever reason the dark matter were a little clumpier, we could see it. Now, we do know that dark matter is clumped around clusters of galaxies from these gravitational lensing measurements. If you look a little bit off to the side, you don't see things gravitationally lensed. I didn't show the picture in this talk, but next time you're at the astronomy picture of the day, do a search on 5 quasar gravitational lens. And you'll see that, like, this strong gravitational lensing where you see the same object many times as the light's bent is it's quite pronounced, and you can, working out how it works, that the dark matter has to be clumped around the visible things that we can see. But it's actually the other way around. The visible matter is clumped around the dark matter. In the standard cosmological picture, it's not that the dark matter is clumped around the visible matter. The clumping started with the dark matter. And you can only make simulations work based on gravity if the dark matter started the clumping early in the universe.
So, one more quick question, going back to what Paul was asking about light and your answer about, it's following a straight path through curved space-time. So dark matter would be warping space-time just like mass does?
Yeah, because dark matter, okay, so in this model of dark matter, yeah, it has mass. And so it is warping space. So all the information we have about dark matter right now comes from gravity. Everything else in these experiments I described that we're doing is just constraining our ignorance. The evidence for dark matter is from its gravitational effect.
I want to thank you, Chris, for joining us tonight. It has been a fascinating talk with everything from curling stones to lensing to an explanation about gravity that was the best explanation, as I said, I've ever heard, to science being so cool and going to work every day and discovering things that aren't there and that you hope to find. I think that's just so wonderful. So thank you so much for coming tonight. And before you go, you have relatives sitting here in the audience, and I want to thank Marcus Freeman for actually reaching out to you and asking if you would join us tonight. And I know you have another talk available for us. And I see some maybe nods in the room about, yeah, we should get him back for another talk. So thank you so much for joining us tonight.
I'm very pleased to have come, and it's nice to have such a large and enthusiastic audience. I really appreciate it. And yeah, so you'll note a theme. My other talk is titled How to Know the Sun from a Hole in the Ground. And I'd be happy to talk about that at maybe next year, a subsequent year in the calendar. I will try to get down in person for it and have some Southern Ontario craft beer with you after the meeting.
We would love to have you come and join us for sure. And just before you go, thank you for mentioning all of the other people who work on these projects with you. I think it's really important that it's not just a scientist that you can be, but everybody else, from plumbers to electrical engineers to electricians to millwrights to, the chemists and everybody else. This wouldn't work without that large team of people. So thank you for mentioning them. That was really important. We're going to take about a 7-minute break. Gary, if you want to go back and see Doug, you can ask Chris your question, and then we will reconvene in about 7 minutes or so. So thank you, everybody, and thanks again, Chris, for joining us tonight.
And I hope it cleared up for you so you can see some northern lights.
Us too.
Chris?
Yeah.
The other Chris in the room, our tech support guy, we need to shut the Zoom audio off in the room so not everyone is, the noise gets pretty horrendous. I'll just make sure that's shut off. Questions? No, I think we'll see. Oh, so there's no I'm sorry for keeping you hanging around here. Apparently, you've already answered the question that was going to be asked at the end of the meeting. So you're more than welcome to stick with us for the Sky This Month presentation that's coming up after. Really appreciate your being with us. But at this time, there's no more questions.
Okay, well, thank you so much. I have a dog who's gonna need some attention from me, so I'm going to sign off and thank you very much. And I'll shoot a quick email after this to Sue. Thank you so much for having me.
Okay.
And enjoy the skies. Keep looking up.
Okay, thank you, and have a good talk with your dog.
Bye-bye.
Bye.
Are you there, Doug?
Okay. We have some controversy up here with the guess the constellation. So Matthew believes that this is M35 and I believe it's M38. And so one of us is going to be right and one of us is going to be wrong. And if I'm wrong, then I'm going to go on WikiSky and tell them that they're wrong. Because Matthew's looking it up right now. So tonight, all right, Robert, pick the first number, please. Oh, he's rooting around in there. He's going to get a good one. There we go. All right. So tonight, oh, now I'm not as loud as I was before. Okay. Now I won't. Now it won't advance. Oh, come on. Don't complicate it any more than it needs to be. Now I can't advance. All right, I'm gonna not mess with that. So tonight we have three books. We have 50 Things to See on the Moon by John Reed. Although this is written for a younger audience, it's still a really useful observing guide for looking at the moon. We have Summer Stargazing by Terence Dickinson. I thought that was appropriate, seeing as the summer season will soon be upon us. And Splendors of the Universe, also by Terence Dickinson, written with Jack Newton. And it's a little dated, but it offers some great tips on taking pictures of the night sky if you are just getting started. So Robert has pulled the first ticket. This one is a red ticket, and the last four numbers are 2074. Somebody missed it by one. 2074. Going once. Going twice. Going, gone. All right, Robert, you got to pick another one. Okay. This one is also a red ticket, 2079. Oh, Tom, come on up and make your pick. You have to pick Roberts now.
Pick mine only again. Pick the next one, and then I'm
What is it?
Okay.
2053.
Right here.
Oh, Jim, awesome. I'll take that one. And
Oh, yeah, take this one.
make a draw. The last one is a red ticket, 2071. Oh, Jeff, there you go. Awesome. Okay. Yeah, that's good. I trust you anyway. The 50 things to see on the moon. Okay. And next up, we have Matthew Mannering, our observing director, who's going to talk to us about the sky this month. And just a second, Matt, I just want to get you. Yeah. It's not working, so you may have to just go from no.
Battery?
Could be. If you give me a second, I have an extra battery. Oops.
This? Testing. So this feels very strange. Anyways, welcome to the sky this month for May of 2024. I'm starting this month with a picture that was submitted by Chris Schaben. Is he here? Chris, oh, there you go. Hi, Chris. And it's of a open cluster NGC 6791. I didn't know about this cluster, so I looked it up. And it's actually quite an interesting cluster. It's apparently a lot of research is done on this cluster because it's very ancient. It's about 8 billion years old. And the scientists find it very interesting because of a couple of things. Number one, there's way too many metals in the stars in this cluster than there should be. So metals in astronomy are anything heavier than helium. So hydrogen, helium are gases, everything else is considered a metal. And those things are produced by generations of stars when they go supernova and as they throw off layers of their surface as they age. And so this is where all the heavier elements come from. These stars are old enough that they should all be basically hydrogen helium stars, but they've got way too much metals in them, so they study it for that. And also, there's another generation of stars in this cluster that's only 6 billion years old, And they can't figure out where they come from because basically there's not enough gas and dust would have been in a cluster this small. It's about 300 or 500 stars. So how do you get enough gravity and enough matter to actually create another generation of stars? So this actually is a really interesting cluster to research if you're interested. 6791. It is just outside of Lyra, the HARP, and it is down here. And you can see it sort of in the Milky Way because Lyra itself is on the edge of what we would consider the Milky Way, the bright star Vega. And there's a couple other things here to look at, the double-double, which is the Tim Hortons double-double. And that one, if you look at that through they're like binoculars, you'll see one star. If you look through a small telescope at low magnification, you'll see 2 stars. And if you look at medium magnification, you'll see the stars are getting elongated. And if you go to high magnification, you'll see each of those 2 stars is 2 stars. So visually, for those who do visual astronomy, this is a really cool thing to look at. And the more you pour on the magnification, the more you see. The other thing is, of course, the Ring Nebula down here, another great visual target. It's quite small and it just looks like a smoke ring in the sky, but I've looked at it a ton of times. I always find it interesting. It's the atmosphere of a star that's been blown off as the star ages, and it's actually quite easy to find. So the HARP itself is this parallelogram here, and Chelyabinsk is this star here, and it's on the same side of the parallelogram as Vega, sort of, you can draw that. And then if you go between the 2 close stars, you go almost halfway from Chelyabinsk, put your scope there, and if it's not in your field of view, just jiggle it around a little bit and it will be there because it's really pretty easy to find. So 6791 is definitely worth photographically doing. It's really pretty. And also it's in an interesting area of the sky. John Govro was a bad boy. He sent me this after I had already put my PC in the car, along with everything, the complete presentation, but it's really cool. He took it this morning. It shows that huge sunspot group there that's been causing all the activity on the news and on the internet and in the upper atmosphere. There's fantastic aurora right now over Europe and coming our way. The KP index is almost at 9, which is very, very high. And it should be quite the show for this weekend. There's been 6 major eruptions. The last one was an X flare 3.9 a couple hours ago. And this sunspot group is about 200,000 kilometers across, so about 15 Earth diameters, maybe even a bit more. It's about the same size as the Carrington group back in the around 1860-ish, whenever that was back then. But 1854, there you go. I was close. I was within a decade. And it's not putting out the same crazy flares that one did, but it's certainly trying. It's really trying. So tonight at 10 o'clock on CNN, they're having a special show about the aurora that's supposed to be happening tonight. So that's very unusual that CNN is not covering some trial that's going on in the States right now. They're actually going to talk about something else. Who saw Pons Brooks, either visually or in the camera or binoculars or any which way? How many people saw the tail? Some aspect of it. Okay, so this is April 5th. Sue, Doug, Janice, and I saw this basically exact same view 2 nights later where the comet was up here a bit higher, but very much like this from a dark location. And we saw a tail that was about 2 degrees long. You can sort of measure stuff like that if you know the field of view of your binoculars, and you can sort of figure out, so half of the field in my binoculars is 2.5 degrees, and I didn't quite get half a field of tail from the comet. So you can sort of say it's around 2 degrees. And it was really a great view. But there's another one coming. In fact, it's already on its way in. And I was going to talk about this anyway, Bob. So you sent me a great picture. This is not Bob's picture. Bob's got a better picture. But this comet, Shushinshan Atlas C 2023 A3. The A3 just means it was found very early in the year in 2023. Anyways, it's coming in. It's inbound from the Oort cloud. It's got an extremely long orbit. I've read anywhere from 10,000 years to 70,000 years, and I don't know which one's correct. Different sources, wildly different numbers. It's coming in really fast as well. It's somewhere between Mars and Jupiter now in terms of distance orbitally from the sun. It is going to come speeding in, and then it's going to disappear from our skies somewhere around, I would say, mid-August. It'll be gone for sure, too close to the sun. If it survives its trip around the sun and doesn't get shredded by the gravitational field of the sun, then it's going to come bombing out the other side. And for sometime around October 10th to 15th, it's going to be visible in the sky at dusk in the west, low in the west. And if it survives, they're expecting a tail that could be just absolutely awesomely long, like 20, 30, 40-degree long tail, magnitude 2. It'll be easily naked eye visible. Now, the one thing that you'll notice is that they do a lot these days, pencil it in, but yeah, use a pencil, because I don't know who remembers Comet Ison. That was going to be the comet of the century that just self-destructed as it got close to the sun, and there was nothing. But this one, if it does what it's supposed to do, could be absolutely fantastic. It's make Pons Brooks look like a little pea shooter in comparison. This is Bob's picture he took just what, 2 days ago, Bob? That's 2 days ago. Nice picture there, and he's even got a barred spiral galaxy up there, and he got a really nice image of it. He said he got it between nightfall and when the fog rolled in, right? So good timing. Obviously, you got enough exposure with it, and you're using a sea star like lots of other people these days. So that's pretty cool. Maybe someday I'll have to get one. Okay, so where is the comet right now? Well, it's in Virgo. So that's easily visible from our skies. There you can see Leo's up here. The green line is the southern meridian. In other words, you're looking due south, and the comet is in Virgo. So we've got months to look at it as it comes inbound before it gets too close to the sun. And then hopefully as it goes outbound again, we'll get a great view. I'm really just scattershot tonight, all kinds of different things. Back in the fall, when we were at the Star Party, I looked at an object called Mirac's Ghost in Andromeda. It's a little galaxy that's so close to Mirac, the star, which is a bright star, that it's hard to see the galaxy because the starlight actually almost drowns out the light from the galaxy. So we all actually saw it, which was really cool. So then I remembered Leo 1. If you go looking for this in your software, what you're going to find is it's called something like PNG or PG something or other. Just all you have to know is there's Regulus, which is the brightest star in Leo, and it's right beside it, just above it. So it'd be interesting to see if anybody with a large scope could pick that out visually or photograph it. We tried last week and we couldn't see it visually because the transparency was terrible. And Janice tried photographing it, and we just couldn't even pick it up that way. But it's very dim. It's about 15 arc minutes across, which is like half a full moon. So that magnitude 10 light is spread out of over a large area. But it's still, I think, if you can get a really dark sky and a big aperture or a long exposure, it'd be interesting to see if anybody can grab it. Now, last month after the this says awesome aurora pictures from Europe coming in now. Full sky display all the way down to the southern Germany, France, Spain, and Italy. So hopefully we'll get to see something. Anyways, last month was right after the eclipse. This picture didn't get in. It turned out it was from the Chatham Daily News. And here you can see Denise and Dan and Chris and Chris and Chris. So that's all at Rondo Park. That's before Ann and a few others made it there. But I know they had a great time. They had a great view, and it doesn't look like it was any warmer here than it was in Quebec. Now, there are some more pictures. When I thought about these pictures, I thought about pictures at an exhibition, which made me think of Mussorgsky, the Russian guy who wrote the music after he went to see the pictures at the exhibition. And I think you'll agree that if he would have seen the upcoming pictures at the exhibition, he would have said, I need more vodka, because these are not your usual pictures, right? So here's Chris White's effort. I'm not sure if he's sticking his tongue out at me or what there. This is Dan doing the frown and then turning it upside down. And this is Chris Chauvin doing the, what do you call that? Chick-fil-A down in the States, that kind of thing there. Oh, so you're the one. I know that. Anyways, they're just fun pictures and very imaginative takes on the eclipse. The picnic and the Perseid night, it's the same day and evening, August 10th, Saturday. It's going to be at Binbrook. We used to have this before COVID, and we did 3 of them maybe. They were huge successes. At the one time we had like 1,000 people come in to see if they could see any Perseids with us. The potluck dinner is going to be at 5:30 at Pavilion 3, which is, I believe, the one we normally go to. The club is not going to provide any kinds of drinks or a barbecue or burgers or anything. This is a complete bring everything that you want to eat or drink or whatever, and hopefully bring something for the potluck, in which case, please bring some spoons or forks or whatever to serve it. But it's always fun. We always have a great time. You can bring your solar scopes, right, and set up. When you get to the gate at Binbrook, just let them know you're with the HAA. Also, we need volunteers for the next part. So when the public starts coming in for the Perseid event, we need people to help with parking vehicles, maybe being at the front gate as greeters. We need people to represent the club a bit later, maybe at a table where we hand out information about the club. And we need people to run some scopes for the evening so that the public that comes in has a great evening that we can put on for them. You can talk to Kevin. Where's Kevin? Oh, well, if Kevin was here, he'd put up his hand and say hi. He's not here. Brenda. Okay. Anyways, or me. So I'm still here. Anyway, so if you send an email to observing@amateurastronomy.org, you'll be able to let me know that you're interested in helping in whatever capacity. So this is always one of our best club events. It would be nice to get back to it again after the years of COVID. Don't have to register? Oh, no, you don't need to let me know you're coming to the potluck. You just have to let me know if you'd like to volunteer for other aspects of the evening. Yes, everybody in the club is welcome to the potluck. You just gotta show up. So another minor detail is that, big surprise, the Starliner did not take off on Monday. They're going to try again on May 17th at 6:16 p.m. exactly. And you'll see right here, it says net May 17th. That means no earlier than. So I actually had to read further down because I couldn't figure out what the heck the net meant, but it means no earlier than. So 6:15 is out, but 6:16 they might actually go. So we'll just wait and see what actually happens. Another big piece of observing news would be T Corona Borealis. This is also called the Blaze Star. Normally, it is a nothing thing to look at through a telescope. It's a magnitude 10, 11, very faint star inside that circle there. Corona Borealis is really well known for having nothing of interest actually to look at through a scope visually. But this star sits there, and every 80 years, it goes boom. It's a recurring nova. And it is due. In fact, it's been due for the last few months, but it was due in a time frame between, say, the beginning of this year through September this year. And it will go from magnitude 10, 11 to about mag 2. It'll be about the same brightness as the main star, the brightest star in Corona Borealis. The sad part is it will stay that bright for about a day or 2 days, and then it will start to dim. It's a very quick event, and I'm going to tell you a bit more about that. So the way T Corona works is that it's a 2-star system. There's a red giant, there's a white dwarf, and as happens with these systems, the white dwarf sucks material off of the red giant, and it forms an accretion disk around the white dwarf, and some of that falls to the surface. And if enough of it falls to the surface over time, in this case, 80 years, what happens is it starts a runaway thermonuclear explosion, and the whole surface of the star goes boom. And of course, the brightness goes up by, 8 magnitudes in an extremely short period of time. But then the light starts to wane almost immediately as well. But it's interesting in that the first time this was observed was in 1217. There's no other documented observations until 1787 and then 1866 and right after World War II in 1946. In fact, they started getting observations probably while the war was still going on. Astronomy didn't stop because of the war. There was still research going on. Now, in the last 2 examples, these 80-year apart examples, there's this really weird dip in the blue light. So in the spectrum of the star, the blue light that we see starts to dip, it gets dimmer, and the star starts to dim in blue, and it goes from magnitude 10.5 to about magnitude 12. Remember, the bigger the number of the magnitude, the dimmer it is. And that starts about 1.1 years before the eruption. And then, so it gets dimmer and dimmer and dimmer, and all of a sudden, bang, and off it goes. So you get your nova eruption, and what they've looked at is in 2023, it started to dim. And so they say, okay, 1.1 years later or so, it should actually go boom. So that is in 2024.4, which would be about 4.5 months, plus or minus 0.3 of a year. So could take you all the way to around September of this year. So sometime between now and then, it should go. I've been looking for any kind of a subscription where I could say, tell me when it goes boom, right? As a message or an email. Other than the Variable Star Association, or I haven't found anything yet, and I don't belong to that. So I'm not sure how we're going to find out if it goes, but if I find out anything, I'll post it through email. So here's some light curves that show you how the blue light since 2023 starting to drop off. This is a B and V chart. So I'm being very careful about how I say that, B and V, because I'm going to show you something in a second that will mix you right up. The V is actually green, yellow light, part of the spectra. The blue is blue. And the green stays pretty much the same, but the blue is what's dropping off. Now, there's something else called a BV color index. It is not the same as B and V. It is an index that they have created with some formula that basically says that blue stars, which are usually the biggest and young stars, really huge stars, they have an index value of -0.3. And as you work your way down through main sequence star types, all the way down to red dwarfs, they get redder and redder until you get to a red dwarf and you get to a number like 1.4. So this is for main sequence stars. If you take into account stars that are past that point and are now red giants, they get to numbers that are well above 1.4. And in fact, carbon stars get up to 4 and 5. So this number is quite a wide range. So what you want to know is that as the number gets higher, the amount of blue light that's being put out obviously drops off, and the amount of red light increases that you're getting from it. So here's that next graph that was in the article that I read yesterday, which I had to think about for a minute before I remembered what the BV was. And here you can see that the light in the index value, which is around 1 here, all of a sudden starts going up. But they use blue. Like they could have used purple or, you know, some other color other than blue, but they use blue. So it makes you think it's the blue light value, which in the other graph is going down and this one's going up. It's because it's a totally different value. That's not really the blue light. It's an index based on some formula that says how red the star is. And as the blue light drops off, the red light that you see proportionally picks up. Yes. Could be. Could be. Yes. And there are other, I took most of this chart away because there's other indexes. There's blue ultraviolet, there's infrared red, there's like about 5 different. A could be, I agree. So anyway, there's all these other indexes, but the only one that we care about is the BV one. It's one of the most common. So just remember, it's an index of how blue or red a star is. And it's not dependent on whether it's main sequence or it's past that. It's just its color. So I've said already, it's going to get to magnitude 2, like just about as bright as the brightest star in Corona Borealis. But within 5 days, it's going to fade to mag 5. It's almost not naked eye visible anymore. And the other interesting thing is there's a secondary eruption that happens about 3 months later and lasts about 3 months. And it will go from mag 10.5, 11, up to about mag 8 and stay there for a few months. Now, I found no explanation for this, but my thinking would be that when you get a blast like this off the star, you're going to get some bounce and some of the material is going to come back. So if that happens, then imagine instead of having a nuclear eruption, you've got like a pot that's on simmer and it's just bubbling away. Well, this is some sort of nuclear reaction that's just sort of burbling away for 3 months. And I think that's the most reasonable explanation for that. This is the 1946 eruption. And here you can see mag 10-ish. Then you can see the drop off in blue light. And then you can see it just goes bonkers. But you can also see it's an extremely tight line up and down, right? It's vertical. Back down to 10, then you get the secondary eruption. And then for another 80 years, it just sits there going beep. So this is really a once in a lifetime. There's only 10 of these in the whole galaxy that are known that do this on this sort of a cycle. So it's extremely rare. And I've got one quick question. I had a question from a new member by email that said, where do you go to observe where it's not so light polluted that, you know, you can't do too much? So I thought I would ask the question because nobody ever seems to ask that question. I know where I go and other people know where they go and some people stay in their backyards, but does anybody have any observing sites that are public, that are reasonably dark within, I don't know, an hour and a half of Hamilton or so? Is there spots that people go that they're willing to share where they go? It's a secret. Okay, if you'd like to share anything, you can send it to observing@amateurastronomy.org and I'll pass it around or bring it up at the next. Oh, no, I'll pass it around because I'm not doing another talk till September. Okay, so that's really about it. If there's any questions, everybody's ready to go home? 9:45. I'm done. Oops.
Hmm. So now my slideshow doesn't want to go. There we go. All right. So thank you very much, Matt, for sharing that. Interesting and fascinating as always. Just a quick reminder, Friday, June 14th, back here with Benjamin Law. Binbrook Observing is canceled tomorrow night, so there's no observing tomorrow night. We'll get that email out. Oh, it's already out. The next opportunity is the 1st or the 8th, then our meeting is on the 14th. The Perseid night, if you want to help out, please let Matthew know. Please come to the picnic. It's a great time. And the Dark Sky Star Party at the end of August. And with that, thank you to everybody for coming out tonight and a safe drive home. And we will see you all next week or next month.